freeze-drying of pharmaceutical and food products. Bale and Lou. Contents Chapter 1. Introduction. Chapter 2. Fundamentals of freeze-drying. Chapter 3. Heat mass transfer analysis and modeling for drying process. Chapter 4. Equipment of freeze-drying. Chapter 5. Freeze-drying of food. Chapter 6. Protective agent and additives for freeze-drying of pharmaceutical products. Chapter 7. Freeze-drying of pharmaceuticals. Chapter 8. Disinfection, sterilization and valuation. In freeze-drying, Chapter 1 Introduction. Freeze-drying is a kind of preservation technology, by which the material is cooled below its eutectic temperature or glass transition temperature, firstly to be solidified completely, then dried in vacuum space at low temperature by sublimation drying and desorption drying till 95 to 99% of moisture is removed. The product can be stored at room temperature or 40°C for a long time. Freeze-drying has become a most important technique for the preservation of heat-sensitive pharmaceuticals and foods. Basic theory of food degeneration. Microbiological action: microorganism growth, bacterium, microzyme, mycete. Chemical action: enzymic reaction, oxidation action and oxidation action of lipase, protease, amylase, pectase and oxidases. Physical action: mechanical damage, inner-outer, inhibited factor of food degeneration. Temperature. To microorganism. Microorganism. Minimum temperature for growth. Optimal temperature for growth. Maximum temperature for growth. Thermophilic. Mesophile. Piscrophile. Psychrophilic. 35 to 45. 5 to 15. 5-5. 10-5. 50 to 70. 30 to 45. 25 to 30. 12 to 15. 70 to 90. 45 to 55. 30 to 55. 15 to 25. To the enzymic reaction velocity. Temperature coefficient of fruit breathing velocity. To the breathing action velocity. Temperature coefficient of fruit breathing velocity. Cat. D/C 010 1121 16.6 26.6 22.2 322 33.3 43.3 Strawberry 3.45 2.10 2.20 Peach 4.10 3.15 2.25 Lemon 3.95 1.70 1.95 2.00 Orange 3.30 1.80 1.55 1.60 Grape 3.35 1.45 1.65 2.50 Microorganism inhibited. Water activity. Microorganism inhibited. Clostridium botulinum E 0.97 Pseudomonas fluorescens Escherichia coli 0.95 Clostridium perfringens 0.95 Salmonella Vibrio cholerae Clostridium botulinum B 0.97 Bacillus cereus 0.93 Listeria monocytogenes 0.92 Bacillus subtilis 0.91 Staphylococcus aureus 0.87 Most fungi 0.70 No microbial proliferation 0.50 to enzyme. Enzyme activity. Water activity, pH value. Effects to food degeneration. Other factors. Effects to food degeneration. Methods to food preservation. Basic principles restrain the growth of microorganism and enzyme action through the physical and chemical factors. Methods. Physical. Drying method: weather drying, freeze drying. Pyroprocess, pasteurization, ultra-high temperature. Cryopreservation, restrain the reproduction of microorganism. Radiation preservation, use ray beta gamma X to kill the microorganism. Chemical. Brine salting, dehydrate microorganism and retain the putrefying bacteria. Chemical additive, preservative, anti-stalling agent, pigments. History of freeze-drying technology. The principle of using of ice crystal sublimation for dehydration have been raised by scholars early in the 19th century. In 1909, Shackle published his report on freeze-drying experiments. The equipment is very primitive: vacuum pump, with salt and ice as refrigerant, sulfuric acid as desiccant. Freeze-dried products are complement, anti-serum, rabies virus, creating a new era of freeze-dried technical research and development in biological products. The first commercial freeze-dryer came out in 1935. Flossdorf and Greaves, respectively, developed relatively perfect freeze-drying equipment and facilities, leading freeze-dried biotechnology from the laboratory stage to the industrial production. Lyophile methods, using cold trap to trap and sublimate water vapor. Cryochem methods, using cheap absorbent like calcium sulfate to trap and sublimate water vapor. Desivac methods, using air pump pumping and sublimating water vapor. In 1940, the freeze-dried human plasma and penicillin were heavily produced. World War II has played a significant role in promoting the freeze-dried technology application in the pharmaceutical industry. After the war, freeze-drying rapidly expanded to a variety of vaccines, medicines and other fields. Until now, freeze-drying technology is still widely used in the pharmaceutical field. FD fruit product, strawberry hominy melon. FD meat product, curry beef biryani rice. FD seasoning bag for instant noodles tea. Worldwide, freeze-drying technology has begun to be used in industries such as synthetic foods, vegetables, shrimp, fried goods, meat, tricholinum matsutake, fish, shellfish and meat processing. Academic development of freeze-drying technology. 1944, the first freeze-drying techniques and theoretical monographs. 1951, 1958, the first and second freeze-dried symposium. 1963, the United States established the GMP, Good Manufacturing Practice, production standard for the freeze-drying of pharmaceutical products. The World Trade Organization decided to implement the freeze-dried pharmaceutical GMP standards in 1969. 1990, the emergence and development of biological drugs set new requirements of freeze-drying technology. 1980, solution vitrification theory and food polymer science theory had provided some theoretical foundation to the development of freeze-drying. The oldest known method of food preservation is drying food using the heat from the sun. 1. Convective drying. 2. Contact drying. 3. Radiant drying. 4. Freeze drying. Convective drying. In the wet material drying process, using hot gas as a source of heat to eliminate the vapor, is convective drying. It is the most widely used drying method. Mainly divided into tunnel-type drying, belt drying, flash drying, fluidized bed drying, spray drying. Contact drying. Dried material was in a state of close contact with the heated surface. Energy to evapor water comes from the conduction of drying. Drying medium can be steam, hot oil. Rapid drying can be realized by using high-pressure steam. Solid materials can be added from 3 to 30% to 90 to 98%, the surface humidity up to 100 to 145 C, Contact time 2 seconds, a few minutes, low cost, with a cooked flavor. Freeze drying, one of the methods of food preservation. Radiant drying. Heat food in the form of radiation, reduce the water. Take the form of ultraviolet rays, electron beam, infrared, microwave, etc. Freeze drying, one of the methods of food preservation. Water-bearing materials will be frozen below the freezing point, from water into ice, and then remove the ice into vapor at a high vacuum. Material can be firstly frozen in the freezer device, then drying, but also can be directly pumped into vacuum and rapidly frozen in the drying chamber. Use the condenser to remove the water vapor generated by sublimation. Heat of vaporization required in the process of sublimation is generally supplied from thermal radiation. Advantages, disadvantages. 1. Keep intact nutrients, such as protein, vitamins, phytonutrients, etc. 2. To retain the original appearance, color and structure of food. 3. Fast, complete recovery after watering. 4. Can be long-term storage at room temperature, without adding any preservatives. 5. Freeze-dried processed foods is light, easy to carry and transport, and lower freight costs. Disadvantages. Higher cost cannot be widely adopted. Used for drying antibiotics, vegetables and fruit, basic processes of freeze-drying. 1. Preparation or pretreatment of the material. 2. Cooling and solidification of the material. 3. Sublimation drying, primary drying. 4. Desorption drying, secondary drying. 5. Conditioning, packing and storage, preparation or pretreatment of the material. For the food materials, physical and chemical pretreatments, which includes cleanout, classification, slice-up, blanching, sterilization, concentration and others. There are differences for different kinds of food. In most cases, it is not necessary to add additive to the food material. For the pharmaceutical materials or the living cells, it is necessary to add some additives, which can be classified as lyoprotectant, emulsifier, bulking agent, antioxidant, buffer agent, and sucrose are efficient lyoprotectants. Cooling and solidification of the material. The cooling process should be done sufficiently. Not only the free water in the material should be frozen to form crystalline ice completely, but also the other constituents of the material should be solidified, to form non-crystalline solid, glassy solid. The solidified material after perfect cooling contains both crystalline solid and non-crystalline hard reticulation structure solid. Sublimation drying, primary drying. For the analysis of freeze drying, the water inside the material can be classified into 2 kinds. One is freezable water and low temperature, which is also called free water. The other kind cannot be frozen at low temperature. This part of water is bound, therefore it is called bound water. Generally it is thought the bound water is adsorbed by the material. For the materials rich of water, the free water will reach over 90% of the total moisture content. Heating is the quantity of heat ice sublimation needed during primary drying. The heating can be done by heat conduction or by heat radiation. 2 basic conditions must be satisfied to assure the progress of the sublimation process. The vapor sublimated must be moved away unceasingly from the sublimation interface. The necessary heat must be unceasingly provided to the material for sublimation. If any one of the 2 basic conditions is not met, some phenomena would appear, such as softening, thawing, bulging or collapsing. In fact, the sublimation drying is a process in which the heat transfer and the mass transfer simultaneously carry on. Only when the heat rate transferred to the interface of sublimation is equal to the heat rate needed for the vapor escaped from the interface, the sublimation drying can carry on smoothly. Desorption drying, secondary drying. After primary drying, there is still unfrozen water adsorbed on porous structure surface and on the polar groups inside the dried material. As the adsorption energy is quite high, Desorption. The bound water also needs higher temperature and enough quantity of heat. In the secondary drying process, the heat needed is the sum of desorption heat and evaporation heat, and it is simply called as the desorption heat. At the end of desorption drying process, the moisture left inside the material is required to reach the remaining moisture. Final RMF. Too high or too low RMF of the freeze-dried material is detrimental. Too high RMF is not conducive to long-term storage. Too low RMF will harm the active material. Generally, the remaining moisture final RMF should be less than 5%. Packing and storage. After primary and secondary stages of freeze-drying, the products must go through conditioning, packing and storage. Sealing and packing should be conducted in dry environment. If no contacting with oxygen or water vapor in the air, the freeze-dried products may store longer. When the product is needed to use, rehydrating it is necessary in most cases. Freeze-drying system constitution. Requirement of ice sublimation to freeze-drying system. The saturated pressure of ice with temperature T/C -70, -60, -50, -40, -30, -20, -10, 0.01 m/Pa, 0.262, 1.11, 3.94, 12.9, 38.0, 103.3, 259.9, 610.62. There are two ways to sublimate the ice to vapor. One is by heating to elevate the temperature, another is by evacuating to reduce pressure. In fact, those two methods are simultaneously applied. For example, in order to make the ice to sublimate at 40 C, the pressure inside the drying chamber must be lower than 12.9 pascals. At the same time, in order to provide the heat which the ice sublimation needs, material must be heated. The sublimation heat of ice at 40 C is 2838.6 kJ/kg. Main components of freeze-drying system. A freeze-drying system is mainly composed of the following components: a drying chamber, a cold trap, a refrigeration system, a vacuum system, a heating system and a control system, etc. Technical requirement of major component. Drying chamber. The drying chamber is the place in which drying process under vacuum carries on. The bottles or vials with materials inside are put on the lower heating plate. There is upper heating plate sometimes. Heating materials can be achieved by the conduction through the lower plate, or by the radiation from the upper plate. Cooling solidification process, or the freezing process. Material may be performed inside the drying chamber. This time there is a refrigerant inside the lower plate. Refrigeration system worked to decrease the temperature of the material. The cooling process may also be performed outside the drying chamber. After the material being cooled completely, it is put into the drying chamber. Drying chamber cold trap. The drying chamber is requested to be well sealed. In some drying chambers, there is a manipulator which can press the rubber stoppers to seal the bottles. Cold trap. It can be put in or outside of the drying trap. The function of cold trap is to provide a low temperature environment in a vacuum system. The temperature of the cold trap should be much lower than the sublimation interface temperature of the material, 20 K or more. The pressure drop is the driving force of mass transfer which presses the water vapor flowing from the interface of the material to the cold trap. The water vapor escaped from the material is condensed into liquid when it contacts with the cold surface of the cold trap, and then is expelled from the system. Refrigeration system, vacuum system. The task of the refrigeration system is to provide a low temperature environment in the cold trap and or in the drying chamber. Here, the refrigeration system may be in various types: mechanical vapor compression refrigeration, thermoelectric refrigeration, or using liquid nitrogen directly. The cold trap is the evaporator in the refrigeration system. For the cold trap with low temperature, the two-stage compression refrigeration cycle, or cascade refrigeration cycle may be adopted. Vacuum system. The task of the vacuum system is to withdraw the non-condensable gases. In the temperature region dealing with freeze-drying, air are non-condensable gases, which would come in two ways. One way is air leaking from the outside atmosphere into the vacuumed system, the other way is air and/or other gases escaping from the food or pharmaceutical material during drying process. Applications of freeze-drying technology. Freeze-drying of microorganisms. The freeze-drying technology of microorganisms, coffee and milk is more mature. A large number of microorganisms have been able to be successfully freeze-dried, such as bacteria, actinomycetes, yeast, filamentous fungi and viruses. The freeze-dried survival of microorganisms is more than 80%. Nevertheless, up to now there are many microorganisms cannot be freeze-dried yet. Even for many microorganisms which are freeze-dried successfully, the freeze-drying procedures are not the same, and the protective agents are not so similar. Freeze-drying of foods. The freeze-drying of fruits and vegetables is emerging and high-value added technology. Application. Freeze-dried foods are high-value added products, regarded as high-quality food, convenience food, leisure food. Exported vegetables and fruits, or in traveling, exploration, navigation and so on. Problems and difficulties. Freeze-drying process is a time-consuming and energy-consuming process. The parameters of the freeze-drying process have decisive impact on the quality of freeze-dried food. Freeze-dried broccoli, freeze-dried meat, freeze-dried onion, freeze-dried carrot, freeze-dried garden radish, freeze-dried parsley, freeze-dried broccoli, freeze-dried meat, freeze-dried onion, freeze-dried potato wedges, freeze-dried chestnut, freeze-dried ginger slice, freeze-dried pumpkin, freeze-dried potato wedges. Freeze-drying of pharmaceutical products. Heat-sensitive products are sensitive to temperature, mainly to higher temperature, such as liposome, interferon, human growth hormone, as well as Chinese herbal medicine. Freeze-drying of human cells. From the 1960s, the survival of platelets reached 85%. They began to carry out a feasibility study of clinical application, but the recovery of freeze-dried red blood cell is lower than 50%. Human cord blood contains a large number of immature hematopoietic stem cells. Compared with the adult cell, the 0-year-old baby's immature hematopoiesis stem cells have the pollution-free, small allograft rejection, low immunogenicity, and its regeneration capacity and speed is about 10 to 20 times of the adult's. Human umbilical cord blood. Other applications of freeze-drying. Freeze-drying technology has found important applications in the preservation of skin, cornea, and bone, and in preparation of the scaffold of tissue engineering products. Also for the preparation of various superfine powders, including ceramic powder, catalyst powder, metal powder, alloy powder and magnetic powder for recording. Freeze-drying technology has also found applications in the new healthcare cosmetics, the biological sample preparation of electron microscopy, the sample manufacture of animal and human organs,